The function idea can be described in a number of different ways. I saw this method of viewing functions some years ago from an old professor. Before we define a function, let us make a couple of simpler definitions. Let's define a relation as a set of ordered pairs. Now, this set of ordered pairs can be a finite set or an infinite set. It could be an infinite set described by the equation idea, or it can be a little finite set of ordered pairs like this. The pairs 1, 2, 2, 4, 3, 6, 4, 8. Now, let's define the domain of the relation as the set of first components. Very simply, the set of the first components in those sets of ordered pairs. So let's go see what they would be. All right, in this set of ordered pairs, the first components, 1, 2, 3, 4. So just take the first components in those pairs, and that's the domain. Okay? Now let's go back and define the range. The range of the relation is the set of second components. So the range is very simply the second item in this list of ordered pairs. 2, 4, 6, 8. Now, with the notion of relation at our disposal and the idea of what domain and range are, we're now ready to define a function. A function is nothing more than a special kind of relation. Now remember, a relation is just a set of ordered pairs. Could be finite, could be infinite. All right. A function is a relation, set of ordered pairs, in which for every element in the domain, for every first component, there is exactly one. That means there is one and there is no more than one. There's one and only one element in the range. All right, now let's expound upon or expand upon the idea of domain and range. The domain is a set of values. It's simply values of some independent variable. And range, values of a dependent variable. Now this independent and dependent notion here is not completely foreign to us. Because after all, when we were constructing the graphs of some equations earlier, notice how we proceeded. We did this sort of thing. Now suppose let's take an equation like this. Now, how did we proceed when we constructed the table of values? The values that we plot, coordinates of points, solution points for the equation, all related ideas here. How did we proceed? Well, we chose x values out of the air, like 0 for x. And then the value of y depended upon the x that we chose here. You see, if we choose x to be 0, then y in this case turns out to be -3. If we choose x to be, let's say, 2, then choosing x to be 2, 2 times 2 is 4 minus 3 is 1. Now, in this sense, we are choosing the x's. So they are independent choices. They're at our disposal. On the other hand, the y values that are listed here happen to be dependent. They depend upon the x's that we chose. So we can think of domain and range in that form. Now, you know, we're talking about domain and range. We're talking about independent and dependent variables. We're not using the words x and y here. Why is that? Well, it's because in equations we can have relationships that involve many different kinds of variables. We can have m's related to n's and r's relating to s's and distance related to time and other kinds of ideas like that. So we don't want to restrict ourselves to just x's and y's. Now, I will use the xy example often, but let us understand that this xy example can be expanded to involve any two variables. All right, let's look at, graphically, I think shows best or easiest, the notion of what a function looks like and what a non-function looks like. And when I'm talking about function here, I'm talking about y as a function of x, the independent-dependent variable relationship. All right, this is the graph of a relationship in which y is a function of x. Now, why is that? The acid test is that, is it true that for every first component there is exactly one second component? That is it true that for every x there's only one y along this graph? Well, let's see. What about for an x right here? For this x, you see, there is only one y partner with it to describe this point on the graph. For that x, there's one y to describe this point on the graph. For an x out here, there's one y to describe a point on the graph. For every x in the domain, for every x, there's only one y partner to describe a point on the graph. Y is a function of x. Here's a graph of a relationship between x and y in which y is not a function of x. Now, why is that? Why does it fail the test? Because for some values of x, for some items in the domain, and I'm saying some, it's just about all of them in this particular case, but if there's just one example that doesn't fit the definition of function, it's not a function. All right. For a value of x such as, let's say, this one, for this value of x, there is a y value that describes this point on the graph and also describes this point on the graph. That is, the graph is composed of, now let's say that this point is the point 1, 4, and that this is the point 1, negative 4. You see what's happening here is that this item, this value in the domain of our relationship is paired with two items in the range. So if one item in the domain is paired with more than one item in the range, then we cease to have a functional relationship. So y is not a function of x here. Now let's look at an equation or two and see if we have the function relationship. That is y a function of x in this equation? Well, to tell, what we might begin to do is to build a table of values. All right, let's build a table of values in our traditional way. We'll choose x's and fill in for y. What we notice in the table of values is this. Every x has exactly one y partner as we are building. Now, do notice this. This x has 3 as its y partner. When x is replaced with 2, 2 squared is 4, 4 minus 1, 3. When x is replaced with negative 2 squared is 4, minus 1 gives 3. Now notice this x and y have the same partner, but that's okay. That doesn't mean we don't have a functional relationship here. After all, every x, this x has one y, that x has one y. The definition says nothing about two different x's having the same y partner. That's all right. All right, what about this one? Y squared is x minus 1. Now notice the difference between the two equations. Here, the y is squared and the x is to the first degree. In the other one, y was to the first degree and the x was squared. All right, now let's go through it the same way. That is, let's start to build a table of values. Pick the first value. Pick a value like 10. All right, if x is 10, then we have 10 minus 1, or 9. So y squared then is 9, but look at what happens. If y squared is 9, then y, by extracting square roots, is plus or minus the square root of 9, or y is plus or minus 3. So this x value is throwing off two y values. That means that when x is 10, y is 3, or when x is 10, y is negative 3. So a single x, a single item in the domain, is throwing off two items in the range. Anytime there's more than one, we cease to have this functional relationship. Okay, so the first one was a function, or y was a function of x, and this one, y is not a function of x. Now, it's helpful in dealing in the function environment to use what's called function notation. Suppose we have this equation. We can write in function notation the same equation this way. F of x is equal to 3x minus 2. Notice the substitution. Instead of writing y, I can write f of x. They are sort of interchangeable parts. Now, function notation, f, in this case, is the name of the function. Now, the function can be named in a number of different ways. Traditionally, the letters f, g, and h are used in naming functions. So this could be a g of x, and it would be the g function. H of x, it would be the h function. So the letter here simply names the function. Now, this notation is read f of x. It doesn't mean f times x. It's just read f of x, the function of x. And it is simply the value of the function f at x, whatever is chosen for x. Now, here's how that function notation comes into play. Suppose we wish to evaluate the function at certain values of x. We can make the request like this. Suppose we write f of, knowing that f of x, see that this is the f function, then f of 4 means in the f function replace x with 4 and evaluate. Well, this would be 3 times 4 minus 2, or 12 minus 2, 10. F of 0 means in the f function replace x with 0 and evaluate. Well, here we would have 3 times 0 minus 2, or simply negative 2. Now, we must understand that the replacement is a blind replacement. We don't care what is in this little parenthesis. Whatever is in that parenthesis replaces x in this expression. You see, it could be another letter. It could be a binomial. It could be a picture of a Christmas tree. F of Christmas tree. Blind replacement, we don't care what it is. This becomes 3 times Christmas tree minus 2. You see, and we can't do much with that. It doesn't imply any kind of multiplication. But the notion is that it's a blind replacement, and that's an important idea. Here we have another function. This is a g function. I've just given it a different name. G of x is x squared minus 3x plus 2. Now, notice that all we're doing here is it's almost like we're defining the behavior of x, the function of x, the behavior of x, the way x responds in our relationship here. All right, g of 0 means in the g function, replace x with 0 and evaluate. So we would have 0 squared minus 3 times 0 plus 2. Well, these two terms go out, and we've got simply 2. So g of 0 is 2. Now, also notice in this process of using this function notation that it can be used in building a table of values. We are, after all, replacing x with 0 and evaluating what we get in the function. So this becomes the y value in the xy pair idea for building the graph of an equation. Let's see. How about g of t? Well, that means in the g function, replace all the x's with t's. So it would simply be t squared minus 3 times t plus 2. Blind replacement. G of x plus 2. In the g function, replace blindly all of the x's with x plus 2's. So we would have, instead of x squared, we would have x plus 2 squared. Instead of minus 3x, we would have minus 3 times x plus 2, and then plus 2. You see a blind replacement. And now evaluating, let's see, x plus 2 squared is x squared plus 4x plus 4. And then multiplying through, I get negative 3x minus 6 plus 2. And collecting like terms, let's see, I have only one second degree term. 4x minus 3x is simply x. 4 minus 6 is negative 2. Negative 2 plus 2, they go out. So g of x plus 2 is x squared plus x. Here's an interesting kind of function. Notice how it's defined. It says f of x behaves this way if x is less than 0, or when x is less than 0. It behaves this way when x is greater than or equal to 0. Sometimes this is referred to as a split domain function. The domain, the acceptable replacements for x, or the set of first elements, the independent variable, all mean pretty much the same thing. All right, So let's evaluate the function according to this notation. F of 5 means in the f function, replace x with 5 and evaluate. Well, if x is replaced with 5, then we fall into this category. For x is greater than or equal to 0, this is how the function behaves. So what we'll have here is 5 minus 1, or 4. So f of 5 is 4. F of negative 3. Well, when x is replaced with negative 3, we fall into this category, where the x's are less than 0. When the x's are negative, the function behaves this way. So f of negative 3 means replace the x with negative 3. We would have negative 3 squared plus 1, or 9 plus 1, 10. What about f of 0? Well, which category does it fit into? Well, let's see. This says x is less than 0. This says greater than or equal to 0. Well, it would fall into this category, and here's how the function behaves. X minus 1. So we replace x with 0. We'll have 0 minus 1, or negative 1. So f of 0 is negative 1. The domain of a function is sometimes implied by the nature of the function itself, and other times it is defined specifically. Here's a case where the domain is defined specifically with the function. Here's our function, and then notice it says, comma, 2 is less than or equal to x, and x is less than or equal to 4. Now, this tells us the acceptable replacements for x. Now, what does that mean here? How does that affect the situation? Well, let's say that we were building a table of values, and we wanted to construct the graph here. Now notice f of x is just playing the role of y. I could just as easily write this as y is equal to 1/2 x squared plus 1. And when I build my table of values, I could just as easily put y in this position as f of x. So f of x and y are pretty much interchangeable parts. When x is 2, now I'm replacing x with 2 because I'm allowed to do that from my specified domain up here. And I'm just going to take the integer values in this domain as replacement values. I could take fractional values, but the integer values are a little easier to work with. If x is 2, then I have 2 squared, 4. Half of 4 is 2. 2 plus 1, 3. So when x is 2, f of x is 3. When x is 3, 3 squared is 9. Half of 9 is 4.5. 4.5 plus 1, 5.5. So when x is 3, f of x is 5.5. When x is 4, 4 squared is 16. Half of 16 is 8. 8 plus 1, 9. Now, what happens graphically? Well, let's plot these points, and we get these 3 points. And composing the graph by just drawing the line, or it's actually not a line, it's a curve that contains those points, I would have this curve. And notice that this is simply a portion of a parabola. Actually, if the domain weren't specified here, and I was just constructing the graph of this function, then it would be a complete parabola. But here I'm specifying a domain, and so I have only a piece of it. So this is just an example of a place where the domain is specified. Well, often the domain is implied by the nature of the equation, and here's an example of that situation. Suppose g of x is the square root of x minus 2. Now, we know just by the nature of this expression that we can't take the square root of negative numbers. We don't get a real answer for that, or a real value. So we know that x can't take on values which are smaller than 2. 2 is the smallest value that x can take on for this to have any meaning. So if I'm going to compose or construct a graph here, then what I would do is begin with x's that are at 2 and then 3, and then I'm choosing convenient values here, and we'll see why. Let's see. If x is 2, you see I have 2 minus 2 or 0 under the radical. The square root of 0 is 0. If x is 3, 3 minus 2 is 1. The square root of 1 is 1. If x is 6, 6 minus 2 is 4. The square root of 4 is 2. Now, I chose the 6 specifically because after this difference is taken, then I can take the square root of the number under the radical evenly. That is, I'll have a square remaining under the radical. Choosing 11 will create that situation as well. 11 minus 2 is 9. The square root of 9 is 3. So now plotting these points, I get these points, and drawing the curve that contains those points, I get this graph. Now notice that the graph doesn't continue in this direction, and it is, because our domain is simply x's that are greater than or equal to 2, and it's simply implied by the nature of the function. Well, take a look at this function. Suppose we're given f of x to be x squared minus 4x plus 7, and we want to find this quotient. This is called the difference quotient, and it's an algebraic manipulation that's useful in calculus. Now, let's go through the algebraic manipulation here. What does this mean? Well, from our function notation, we understand that this part says f of x plus h means in the f function, replace all the x's with x plus h's. So, here's our f function. We'll replace all those x's with x plus h's. Blind replacement now. X squared then becomes x plus h squared. Then minus 4x becomes minus 4 times, we're replacing that x with x plus h. And then plus 7. So this part represents f of x plus h. If I separate it from the other part, to emphasize its separation, I might do this. Now I want to subtract f of x. I'll subtract whatever f of x is. Well, f of x is this. So it is x squared minus 4x plus 7. And there's my numerator. Now all of this is over h. And it doesn't say f of h, it simply says h. So let's put an h here. Now we simplify. X plus h squared. Well, let's see, that's x squared plus 2 times the product of these two, which would be hx plus h squared, minus 4 times x plus h, that's minus 4x minus 4h plus 7. Now, the negative 1 times every term in the parenthesis simply changes all of the signs, so I get minus x squared plus 4x minus 7, and all of this is over h. Let's collect. Let's see, we have x squared here and a negative x squared over here, so those will take each other out. All right, let's see what else we have. We have an h squared here, which I'll bring down. I've got now my first degree terms. Let's see, involving x, I have 2hx here. I have minus 4x. I have 4h. I have a 7. Oh, I see a cancellation. The 7 and the negative 7 take each other out. I see a 4x here and a negative 4x here, so those go out. Now all I'm left with then is these three terms. I've already written down the h squared, so I'll bring down the plus 2hx and the minus 4h. And all of this is over h. Now, I can get a cancellation if I factor the h out of that numerator. Let's go up here and do that. I pull the h out of that numerator, and I've got, let's see, h plus 2x minus 4. Pulling the h out of each term, you see. And all of this is over h. The h is canceled here, and I've got h plus 2x minus 4. Now, this might seem like a lot of manipulation, but to deal with it, all we need to do is write large and be organized, be able to look at all of the operations involved and collect the like terms and just be safe with what we're doing. Just don't try to skip any steps, and it works out fine. an example of the point plotting